Range anxiety is real. It is the fear that your electric vehicle will run out of charge before it reaches its destination. And it is considered to be one of the biggest blockers for the mass adoption of electric vehicles. We have set this demo up to illustrate how Kinetica's Graph API, coupled with its computational power, can be used to find optimal routes between a source and a destination point with stops at a charging station. These time-lapse videos show shortest path computations that are being performed every 5 seconds on new source and destination points. Shortest path solvers are used to find the optimal path between 2 points on a graph network that has the lowest combined edge weights. Edge weights can be used to optimize for things like distance, the time taken, or even something random, like say how scenic a route is. We can pretty much model anything as long as we have data on it. So the shortest path solver is used to find the best path from a particular source to a destination point. So why are there 3 maps here? Well, that's because we are trying to solve a problem that requires us to apply the shortest path solver twice, and then combine the results to find the optimal path. Let's look at a simplified illustration of the problem to understand this better. I'm Hari Subhash with Kinetica, and in this video, we will solve the following problem. We are in an electric car that is almost out of charge, and we want to find the best route to get from a source point to a destination point, but with a stop at a charging station before our electric car runs out of charge. But here's a slight complication. We have multiple charging points that we can select from. So which one should we pick for this route? Our first thought might be to pick the charging station that is the closest to our starting point. But this might not always be the best choice, because it doesn't factor in the trip from the charging station to the destination. So to solve this problem, we need to compute all the shortest paths from the source point to all the charging stations that we can get to before we run out of charge. Next, we need to find the inverse shortest path from all the charging points to the destination point. And finally, we need to use the output from the 2 shortest path solvers to find the route with the charging station stop that has the lowest combined weights. This is the best or shortest path in terms of time from the source to the destination point that includes a stop at the charging station. Now that was a simple illustration of the problem and the steps we need to use to solve it. The actual example is far bigger in scale. For each iteration, we will be selecting from 268 charging stations instead of the 4 we saw just now. And we'll be working with new sets of source and destination points every 5 seconds. Our graph network is also really large and has more than 1.2 million nodes in it. And we're going to do all of this using just a small instance of Kinetica. But before we start, I want to say that this demo is fully reproducible. So you can use the link in the video description to download the workbook from GitHub and try this out on your own using Kinetica. This is Workbench, an interactive tool for managing your database and for analyzing your data. Let's open up the workbook with all the code for running this demo. Workbooks are split into worksheets, which are a convenient way to organize your work. Let's start by running all the code in the data setup sheet. This will set up the schema, the data sources, and the tables into which the data will be loaded. Now let's head over to the Data tab to explore these tables. Tables in Kinetica are organized into schemas. We will be using 3 different inputs for this analysis. First, we have a large table that contains information like the direction, the average speeds, time, and WKT lines for the road segments that comprise the road network in and around Detroit. WKT, or well-known text, is a popular format for representing geospatial objects, and WKT lines are used to represent geospatial lines. Next, we have a table with the lat and long columns that specify the locations of the 268 different charging stations. A third and final input table is for source and destination points. The input for this is a Kafka topic. Right now, the table is empty because it is waiting for new messages to hit the topic. We can check on it later to see if the data is coming in. Now let's take a moment to understand the general architecture here. First, we have the static data source, which is an S3 bucket on AWS. The road network and the locations of the charging stations are stored here. Next, we have a streaming data source via Kafka. We've set this topic up as a way to simulate how a web app or a BI tool might send in new sets of source and destination points via Kafka into Kinetica. Our first step is to register these data sources, and then we ingest the data from these sources into Kinetica. Once the data hits Kinetica, we use the Graph API to find the optimal route for new sets of source and destination points that are streaming in from Kafka. Although we haven't covered this in this demo, Kinetica also makes it easy to plug into these outputs for downstream analytics and decisioning systems. Now that we have our input table set up, let's move on to the analysis. Our first task is to create a graph that represents the road network data. This query creates a directed graph with weights. The edges of the graph are specified using the duplicate lines. The direction column specifies whether an edge is one-way or two-way, and the time for traversing an edge is used as the weights on the edge. While Kinetica uses an internal representation of the graph to perform analytical tasks, you can also generate an optional output table, which is handy for inspecting the graph and visualizing it using the map block. Let's run this select statement to see the first few rows in this table. The map below is already configured to display the graph using the optional table above. Let's refresh it to see the graph on a map. You can update the map block using the options here. Clicking on the graph will also display the information from the input table corresponding to a particular edge. You can also use the Data tab to see more information on the graph. For instance, you can see that this graph has more than 1.2 million nodes and edges, and it takes 116 megabytes of space. Now let's set up the queries to find the best route. The first thing we need is a table that will hold the final output. Let's also check to see if the data has started coming into the source and destination table from the Kafka topic. Okay, so that is working as expected. Next, we will create a SQL procedure. A SQL procedure is an executable batch of SQL statements that can be run either on schedule or on demand by the user. This batch of SQL statements does the following. Step 1 uses the shortest path solver to find the shortest paths from a given source to all EV charging stations that are within range. Step 2 finds the shortest path from all EV charging stations to a destination point. And finally, we combine the outputs in step 3 to find the best path from a source to a destination point with a charging point stop. This SQL procedure is set to execute every 5 seconds. So every 5 seconds, it is taking in new sets of source and destination points and repeating these calculations. Now let's check out the output from the SQL procedure. The first map shows the output from step 1, that is the paths from the source to all charging stations. The second one shows the path from charging stations to the destination. And finally, the third one shows the combined path, that is from the source and destination point with the charging point stop. These maps are set to refresh every 2 seconds. So every 2 seconds, it goes out to fetch the latest output to update the maps. This may at times lead to a temporary error if the refresh coincides with the execution of the SQL procedure, but it will go away as soon as the new output tables are available. So there you have it. With just a few simple queries, we created a graph and an entire analytical pipeline that takes in data from static and streaming data sources to dynamically create the best routes from a starting point to a destination with a stop at a charging station. Now we can set up downstream analytics using either Kinetica or a custom application to take in these results from the computations and make decisions based on them. Kinetica makes all of this really simple. Everything is done using SQL and with relational tables. There is no complex data engineering required. But the simplicity also can sometimes hide how awesome this really is. We are running computationally expensive analytical queries on a large graph network every 5 seconds using just an extra small CPU-only instance of Kinetica. This is not easy. And if you're interested, check out the video above to learn how Kinetica achieves this kind of performance. And don't forget to try this out on your own. We have a link in the video description to download the workbook and run it on your own. Thank you for watching.